Okay, so it's believed that as many as 25% of adults over 50 never graduated from high school. We wish to see if this percentage is the same among 25 to 30-year-olds. How many of this younger group must we survey in order to estimate the proportion of non-grads to within 6%? What's that going to be? 0.06 is the margin of error, right? And 90% confidence, that means Z star is what? 1.645. Okay. And we're going to use p hat 0.25. It gives us a proportion to use, we're going to use 0.25. If it does not give us a proportion, which one do we use? 0.5. 0.50, right? 50%. Okay, so my formula, margin of error, is Z star times the square root of p hat q hat over n. Margin of error is 0.06. We said Z star is 1.645. And times the square root of 0.25, 0.75, and n is what we are solving for. Okay. And then we do some algebra. We divide by 1.645. Okay, I'm going to pull up my little video of my calculator here. Okay. So in my calculator, 0.06 divided by 1.645 is 0.036. .0365 equals the square root 0.25 times 0.75 is what I'm going to do in my calculator. Is 0.1875 over n. Okay. Now we're going to square both sides. Shh. We square both sides to get rid of the square root, right? This is where a lot of times, nope, I squared the wrong number. I need to square this number. Sometimes this is where I normally will get scientific notation. Okay. If I do, I want to make sure I use like second answer, and I'll show you how to type it in with the EE button in a second. So I get 0.00133 equals 0.1875 divided by n. And now we basically cross multiply, all right? I'm going to multiply the n up and divide by the 1. So n is 0.1875 divided by 0.00133. So I'm going to do 0.1875 divided by second, and then above the negative is answer. So we can just say divide this number by the last thing I got. That's really important if you get scientific notation. And it's really important in getting the most accurate answer. So we get n is equal to 140.93, and we round up to 141. Okay, now look at the, above the comma is the EE button. Okay, so if this is in scientific notation, say it's 0.0365 divided by 1.33 times 10, I do second EE, and that makes it times 10 to the power, and the calculator knows you're talking about scientific notation. If you write times with this button, 10 to the negative power, it's going to do the division and then multiply it by like 0.00000 whatever. And then you're not going to get the right answer. So it's times 10 to the negative 3. If I move that decimal point 1, 2, 3 times, right? That's how you write 1.33 times 10 to the negative 3 in the calculator. We have to use EE. That's the way the calculator displays it, and that's the way you have to type it in if you're going to type it in yourself. I think using the answer key is probably the best, right? Or using the scroll up and divide. But see, then I didn't get the same answer. What the heck? Oh, I didn't square it. Wait. I divided the wrong number. 0.1875 divided by 1.33 e to the negative 3. There you go. Off just a little bit because I rounded this. Yeah. Yes, the quiz will be on paper. Let's stop. Oh, wait, I have to. Okay, so that's the important thing with the times 10 to the 20 negative powers. You have to make sure you are using the EE button, not just typing times 10 to the, it doesn't work that way in the calculator. Okay, then part B says, suppose we want to cut the margin of error to 4%. What's the necessary sample size? Okay, well, how does that change this calculation? Everything stays the same except for this becomes 0.04 times the square root of 0.1875 over n. Right, I already did that calculation. I'm just going to do it real quick. Then I can get this in the calculator. 0.04 divided by 1.645, square it. 1.875. Okay, again, here now we have that scientific notation, right? So if I type in times 10 to the power, it's not going to give me the right answer. So divided by, either scroll up and hit enter or second answer. Okay, start using second answer. There's no reason to retype stuff, right? And I got 3,171. 0.1875, sorry. Oh my goodness. Okay, hold on. 0.1875 divided by this. Enter. There we go. 317.11, 318. Okay. And then the last one asks, what would it take to divide the sample size or your margin of error to 0.03, which would be dividing it in half, right? The original problem said 6%. How much is it going to change if I want to cut that in half? So 0.03. Yes. Part C asks, what sample size would produce a margin of error of 3%? The starting margin of error in this problem was 0.06. I want you to see, okay, the shortcut on some of this. Okay, you are expected to know that. Okay, if 0.03, guys, too much talking, divide by 1.645, square it. 0.1875 divided by this. Okay, I got n equals 564. Okay, so I got 564 and I got 141 originally, right? It was 4 times as much. Why? And it's exactly 4 times as much with my rounding. Okay? So if I want to cut my margin of error in half, I need to multiply my sample size by 4. Right? Because what do we know about where n is in our formula? N's down here, right? When I put a 4 here, what's the square root of 4? 2, and it's in the bottom, right? So half, multiply it by 4, right? So to cut margin of error in half, we have to multiply n by 4.
Is it ever going to ask like a different value than a half?
What do you think it's going to be for to cut it in a third?
No,
9. We have to multiply by 9 because the square root of 9 is 3, right? That number's in the bottom of the fraction, so that becomes 1/3 of the margin of error, that sample, that standard error. I couldn't think of that name. What do you think for 1/4? You have to multiply by 16. What about 1/5? 25. You get the pattern? Okay. So if it asks you, and it will, what if this study had the sample size of 100, and I want to cut the margin of error in half, what will the new sample size be? We shouldn't have to calculate that. We don't even need to know P or the confidence level. None of that matters. We have to multiply. If I want to cut it in half, we multiply the sample size by 4. If I want to cut it by 1/5, then I multiply the sample size by 25. Okay, so it has that squared relationship because n is under the square root. Okay. Okay, so let's get to our cookie game. Okay. I have cookies for you. Chocolate chip and sprinkle. Okay. And I wasn't recording here. All right. So here we have cookies. Here we have a deck of cards. You can see the seal. Do you see the seal?
Yeah,
Brand new deck of cards. Okay. I'm going to pause it while I shuffle. Okay, the only rule of the game. All right, so here we have. I don't want that. Hold on. What the heck? Oh, I have to put up a new window in there. Okay. No, I don't think she needs to see this part. That's just too hard. So you started to question whether or not the deck of cards was fair, right? Because we had the first one half chance, right? And the second one 1/2, and the third 1/2. At here it's 1/8, 0.125. You're like, that's really unlikely. I mean, not too unlikely. But then we did it again, 1/16. Then we did it again, 1/32, and you're still not getting a red card. The probability of that happening is getting smaller and smaller and smaller, even though they're independent, right? So what happened was we came into this with a hypothesis. What was our hypothesis?
The entire deck was black.
No, that wasn't your initial hypothesis.
Oh, at the beginning, half was half.
Your initial, the probability of a red card was 1/2, right? That was our initial hypothesis, okay? You went into the game thinking she wouldn't do us dirty like that and not have any red cards in there, right? It's of course a fair deck. So the probability of getting a red is 1/2. That's what we call our null hypothesis. Our initial hypothesis, okay? So we denote it like this, H0 equals P equals 1/2 or 0.5. Some of it is in the PowerPoint. I will pass that out. Then we did our experiments and our sample proportion was small enough, thank you, to convince you that I was lying, right? The probability of what you saw happening was too small for you to keep believing that it was a fair deck, right? And so you rejected that hypothesis that it was a fair deck, and the probability of a red was 0.5. Yeah, there should be 2 papers for each. Sorry. We have an alternative hypothesis, HA, And that would be that it's not equal to 0.5. Okay. Most of the time, you can never really say that the alternative is true. We could with the deck of cards because I showed you, right? But what you did was our probability of our sample was too small for us to believe it is just random sampling variation. No way. No way, you said, in a real deck of cards, a fair deck of cards, do we get 1, 2, 3, 4, 5, 6, 7, 8 blacks in a row, right? That's 1 over 256. Okay. We've started, but again, we're replacing the card, right? It's even more. The probability would be different if we put the card back in, but still would be very unlikely. If you keep getting black cards, cards, it's more likely that you're going to get a red, right? Because there's more reds in the deck, right? Which is why we had to put the card back so that we could keep the probability simple. Okay, so we rejected the null hypothesis. There was enough evidence, you saw enough evidence to convince you that that deck was not fair, right? Started saying, ha, the deck's all black, really early on. And then it became more like, wait a second, okay, no way. And as it kept going, you got more and more convinced that the deck was not fair, right? So the smaller that probability is of our sample, probability of our sample happening, the more convinced we are that the null hypothesis is not true, right? Okay. So last year it was get a black cookie because I made the deck all red. This year it was get a black card, get a cookie, right? Because the deck was all red. The interesting thing is, one year I did the experiment reversed, where I said it's an all black deck, and if you got a black card, you got a cookie, right? No, everybody got a cookie, right? Because in the black deck, every time you pulled, oh, I got a cookie. It took a lot longer for people to start questioning me because they didn't want to speak up. They were getting cookies, right? People didn't want to call BS on me on not being a fair deck because it didn't matter. They were getting a cookie. And the experiment didn't work as well. So I have to deprive you of the cookie to make it work, to make you start calling and questioning the makeup of the deck. It was very interesting that year. I'm like, I'm just going to see what happens. So we start with that null hypothesis. I'm not going to read through everything on the slide, okay? You can read that yourself. I'd like to get through to actually doing a problem, okay? So our null hypothesis, though, is that nothing has changed. It is what it should be. The deck should be fair. There's no difference. There's no relationship. Okay, it's what we're assessing with the hypothesis test. And we call the proportion P naught. The little subscript 0 is pronounced P naught for our null hypothesis H naught equals P naught. Okay, so we're going to write little equations for this. Our alternative is that the null hypothesis is not true, and it's either greater than our proportion, less than our proportion, or not equal to, depending on how the question is worded. Okay. If it asks if there is a change, just a change, we're not interested in which direction, then it's a not equal to alternative. If it says, is it higher, then it's greater than. Is it less than, right? Is it lower, then it's less than. When we do a not equal to test, we're actually doing a two-tailed test, more like a confidence interval, where we calculate the area Our tests now are calculating the area outside of that value. And it's two-tailed with a not equal to and one-tailed with greater than or less than. It'll make more sense once we start doing examples. So here is our plan, our steps. First thing we have to do is, right now we only have two tests in our arsenal. We have a one proportion confidence interval, which can be used for testing a hypothesis, or a one proportion z-test. Okay, so we have a z-interval and a z-test. This chapter 19, is going to be all z-tests. Okay. Later we're going to have a lot more to choose from. We have to write our hypotheses, check our conditions. The conditions are the same. The only difference is when I check success-failure, I'm checking success-failure not with my sample proportion, but with my hypothesized proportion. Okay. If I'm pulling from the deck 20 times, I expect 10 successes, because that's what I believe is true until I have proven otherwise. So our success-failure has to be based on our hypothesized proportion. Still looking to make sure we think independence is reasonable by checking random sampling and 10% condition. We have to name our test. Since the conditions are met, a normal model is appropriate. I will use a one proportion z-test. It's one of the 4 things they look for and grade you on the AP free response questions, is checking conditions and naming the test by formula or name, identifying the test by name or formula. It's way easier to memorize the name than the formulas. Then we're going to write down our statistics. Then we're going to draw a normal model to kind of see what we're looking at. And then we're going to calculate the mechanics, which is a z-score. Okay, we calculate a z-score. Do we know how to calculate a z-score? We absolutely do. Do we know how to find the probability of that happening? Normal CDF, right? That number that comes out of normal CDF is now called a p-value. Okay, the p-value is the probability of our sample. Tell me if this sounds any familiar, or at all familiar. It's the probability of our sample if the certain proportion is true. In chapter 18, we wrote out our answers that way. There is a blank % chance of obtaining this if the true proportion is that. Why? Because that's what our p-value means, and that's what you're actually calculating. Okay? If the p-value is really small, for our cookie example, our cookie game, the p-value was really small, 1 out of 256. We rejected that null hypothesis that it was true, right? That it was a true fair deck of cards, right? So if the probability is small enough, we don't really believe that that hypothesis can be true, and we reject the null hypothesis. But if the probability is higher, we fail to reject the null hypothesis. We never actually accept the null hypothesis, okay? Because another sample can come along and cause us to reject it. So it's just you reject or we fail to reject. We never accept. We have to calculate z-score and the p-value. Even if we use the calculator, we have to state proper formula with the substituted values. We are going to create our conclusion. We'll talk about how to write that. These are some examples, right? We'll get there. And then to reject or not to reject, we state that decision. If our probability is low enough, we reject the null hypothesis. If the probability is high, we fail to reject. Okay? Think about the example every time you're deciding which one it is, because most people forget or get confused with whether they're rejecting or failing to rejecting. The probability of getting that many black cards in a row was so small, you started to call BS on me, right? You said, no, you were rejecting the fact that that was a fair deck, that that probability was 0.5, because the probability was low. If it was going back and forth between cookie, no cookie, you would be like, well, I have no reason to believe that this isn't a fair deck, right? When we fail to reject, that's the idea. Well, I have no reason to believe that that's not true, right? I don't know for sure, but I have no reason to believe otherwise right now, okay? And then we interpret our conclusion in proper contexts. If we rejected the null, then we can usually create a confidence interval to state what we think the true proportion is. Based on my sample, this is what I believe is true. I don't think it's what we hypothesized. I think this is the new proportion. Okay? Example. Okay. We won't probably get through all of it, but cookies smell really good. We'll have some breakfast later. I didn't. Okay, so I know there's not a lot of room for you to write. I figured you didn't really need a lot of lines next to these, so I consolidated into like smaller paper, right? So you probably should, you could cut that out and put it in your notebook, right? And then write the example under it, because there's not going to be enough room. Well, maybe on the back you might have enough. However you like to do your notes, you know I don't grade them, so. A 1996 report from the U.S. Consumer Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. Okay, so when it talks about some kind of national organization or big company making a claim, that claim is our null hypothesis. Okay, so we're going to test to see what we believe is true about this. Let me get a white pen. Okay. A city's fire department has been running a public safety campaign about smoke detectors with posters, billboards, and ads on radio and TV and in the newspaper. The city wonders if the effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes. Find that 376 have a detector. Is this strong evidence that the local rate is higher than the national rate? Okay. A lot of notation going on here, okay? We're going to start by writing our null hypothesis, HO. Our null hypothesis, H naught, is that P is equal to 0.9 or 0.90, however you like to write it. Your null hypothesis always says equals a value. It is never anything but equals for the null hypothesis. Okay? It's the alternative that takes the same statement and says greater than, less than, or not equal to. Okay? What is the question asking us? Well, yes, that's our sample, but the question's asking it if it's above 90%, right? They're hoping that they have more than 90% of their residents, right? So the alternative hypothesis, we write H sub A, P is greater than 0.9. It's not greater than or equal to, because if it was equal to, that's our null, so we just put greater than, okay? These numbers should, always be the same. Okay, I never change these numbers. It's 0.9, 0.9. The only thing that's changing is the null hypothesis is equal. The alternative is either greater than, less than, or not equal to. Okay. Then we'll check our conditions. Well, what do we have? P hat is equal to 376 out of 400. So that means N is 400, right? 94%. So our conditions, 400 should be less than 10% of all homes in the city. That's probably pretty reasonable considering the fire department had enough money to run ads and billboards and posters and radio and TV commercials. That's a big fire department, right? They're really trying to make a big effort. So it's reasonable to say that's less than 10% of all homes in the city. Does it tell us the sample was random? 400 randomly selected homes. So sample was random. Okay. Now, we have to check NP based on the hypothesis. So if I think that 90% is true, how many homes do I expect to have a detector? So that's 400 times 0.9 has to be greater than or equal to 10. And 400 times 0.1 has to be greater than or equal to 10. Make sure we use the hypothesize P, not our sample. No, it's not. Our sample is 0.94. Our hypothesis is 0.9. Because the national rate is 90%, and this city, the sample gave us 94%. Yes, we understand that 94% is bigger than 90%. But is that a significant enough difference to say that the whole city is higher than the national average? Because that's just a sample. Another sample could come by and give you 89%, right? So is that difference sampling variation? Or did we actually raise the rate in that city? Okay. So that's 360 and 40. Oops, I forgot my 0 on that. So since conditions are met, a normal model is appropriate. And now I will use a one proportion z-test. Yes?
So it's the same conditions as what we were doing.
Yep.
Chocolate, but at the end we just
Say z-test. Same conditions. The conditions aren't actually going to change this unit at all. Okay? The difference is I can't say 376 because that was my sample. I want to know if this is true. We're operating under the assumption that this is the true P. Okay? Then my standard deviation. Okay, my standard deviation is the square root of P naught Q naught over N, which just means we're going to use our hypothesis for our standard deviation. Because until we know otherwise, we believe it's still 90%. So everything we're doing in a hypothesis test is based on the fact that we believe the null hypothesis is true until we get to the end of our process.
And if it's not true, you just do the whole process again with different numbers?
No, we'll just create an interval real quick because our conditions have already been checked. So we just have to create an interval and then say this is what we think it is. Okay? So to be continued tomorrow.